Okay, so let's talk about the change of surface. What's the surface? Surface, yeah? Your skin is the surface of your body, right? So when we have some body, it has a surface, right? For example, let's say this body domain is omega, and it has a surface. This is surface, right? But that's the external surface. But this body can have a surface, internal surface. Okay, for example, if you cut this body, we can have a surface, internal surface. So, inside of body, we have a lot of surface. It depends on how we cut this body and which direction. So, for example, we can cut this body like this also. And there are a lot of ways to make and define the internal surface, right? So we need to think how we can define the surface. So people like to use a vector to define the surface. Surface can be defined by vector. So, for example, let's say vector dA. Let's say just A. And A N. Surface can be defined by a vector, which have a magnitude and direction. So, magnitude means area. And direction means normal direction. Direction normal to surface. So in mechanics, when we define surface, we are using vector. So for example, let's define this internal surface, which have an area A, and its normal direction is N. And also, external surface can be also defined by its normal vector and area. So, surface and area is different, right? Area is a scalar, but surface is a vector. Maybe this could be a new concept for all of you, but very important in mechanics. Yeah. Now let me think of a change of surface. So we have a initial body and we have a deformed body here. And let's define very small surface here, which have an area dA, and its normal direction n. So here initially we have a very small surface vector d a n, and after deformation that area of surface will be changed, right? Let's say this is a small dA, and its direction will be changed also. And let's say the position of this surface is same. So I mean the surface we have this position is moved to this position. So here I like to find out the relation between these two surface vector in initial position and current position. So what I wanted to do is calculate the relation. Let's consider in this case some cylinder, something like that. And here, that cylinder, that's the cylinder have some volume. In this case, that cylinder can be changed. Something like that. And this is a dA, this is a dA. And it has a direction, let's say this is lambda, and it has a direction mu. So originally lambda is a normal to have a same direction to the n, normal direction, but that direction could be changed after deformation. So in initial stage, initial configuration, the volume of that cylinder is a dA and dot product lambda. This will give us the height of the cylinder, right? When we calculate the volume of cylinder, this is the area of the base, and this is the height. And how about d omega t equal dA and and multiply dot product mu. Here we know the relation between two vector mu and lambda. Mu equal f lambda, right? This is deformation tensor. So this vector is changed to this small vector. This is from the definition of deformation vector, right? Understand? Here, very important thing we need to understand is that n is not same to the f n. right? So the originally normal n was a normal vector of the surface at initial configuration. Does not normal at the current cannot be a normal, right? In general, at the current configuration. Okay. So now let's use that relation. So this equation become dA and dot product f lambda, right? And then we know the relation between two volume, right? This was a equation I gave you in the last class. And we are using J instead of a determinant F. J is a determinant F, so same thing. J is a determinant F. Okay, then let's put the result. This one and this one into this equation. So let's say this equation is 1, 2. So put the result here, 2, here, 1. So equation 2 become dA n dot product f lambda equal J dA n dot lambda, right? So okay, and also we can write down this is dot product. So for example, here we have a vector A, B dot product is same to the A, how can I say, transpose B or B transpose A, right? You understand this relation, right? So this equation can written F lambda transpose dA n equal lambda transpose J dA n. And this left hand side F lambda transpose F transpose dA n. So equation just looks a little bit complicated, but you can follow the older procedure. N. Okay, so here we can delete lambda. at both sides. And finally, we can have a dA, this is final equation, and equal F transpose, and its inverse, -1, inverse matrix. J, determinant of Jacobian, dA, n. Okay, this is our final result. What's this? This is a surface vector at initial configuration. This is surface vector at current configuration. So, in other words, dA equal F minus T J dA. Same thing. Okay, minus T means inverse of transpose of matrix F. Okay. This is a very well-known equation, and especially in ocean system engineering, this is very important. When we are using this, yeah. So I like to give you one example. Let's say we have a body here. This is a floating body. And pressure is always normal to the surface. So this is surface wave. And if the body move, the normal direction is changed, right? So we are saying this is a deformation dependent road. So direction of external force is changing depending on the deformation, right? So when you calculate that kind of a changing varying load, okay, deformation dependent load, we need to use this relation. So this is a very important characteristics of water pressure. And this water pressure, some of this water pressure give us buoyancy, right? Buoyancy make some floating structure float on the water, right? Okay, so let me give you example. Let's reuse the example. So this is the original body, omega, and this was a current body, omega t. So we had a deformation tensor F was, I remember, 1 plus alpha, 1 minus beta, and 1. And other members are 0. This was a deformation tensor, if we remember. Okay, and let's say, and we have a initially surface dA, this is a dA vector. Initially, dA equal a very small area, dA, and direction vector n. And let's say direction vector n equal a square root 2, 1 over 2, 1. Okay, this is E1, E2, 1, 1, 0. This is a direction 45 degree. So this is a vector, direction vector n. Then we can calculate how the direction of that vector and area of that surface vector is changed by using that equation. So, sorry. It should be a uppercase n, right? A. Okay, so what we need to do is calculate of dA and dA and n. I wanted to calculate both. And based on that equation, equal transpose of F. Okay, 1, 1 plus alpha, 0, 0, 0, 0, 1 minus beta, 1, 0, 0, 1. And determinant of J, 1 plus alpha, 1 minus beta. And dA, dN. And dA, and N. 1, 1, 0. This is result. Then, okay. Zero. Then we need to normalize this vector to calculate the vector n. Okay, then how we can normalize? Equal root 2 dA square 1 minus beta square plus 1 plus alpha square 1 minus beta 1 plus alpha 0, and I need to multiply also 1 minus beta square plus 1 plus alpha square. So all of this term is equal n direction, and other three gave us a magnitude of the surface. dA. So originally the area of surface is this one. The area is changed, right? By the square root 2 and this one, both. And direction is also changed. Originally 45 degree, but it depends on beta and alpha, how much stretched, right? So originally 45 degree, and after changing, so the degree will be reduced, right? So this is just a geometry, right? This is result from all the geometry, right? So I like to summarize some results we made before. Summary. First, mapping relation between material position at initial configuration and current configuration. And second, from this mapping, we can find out the relation between material vector F, and we defined F, deformation gradient tensor. And third, volume change J, force surface, change of surface. This is a material point. And material vector, volume, surface. Any question? let me talk about polar decomposition. Polar decomposition. And let's consider only 2D case. So E1, E2. And in this case, we have some material body looks like this. Okay, this is omega initial configuration. And after some time, this body rotate without changing in the shape, rotate. So let's say rotate theta. Some body rotate without change of the shape. What's this? What's the name of this? This is rigid body rotation, right? We are saying this is a rigid body rotation. So this is a current body. So what I wanted to do is that to find the mapping relationship in this motion, rigid body motion. Okay, so for example, let's say we have some point here. This point will move to here. Let's say, so we have originally position x, x1, E1, plus x2, E2, plus x3, E3. This is the initial position. So here, x. And this is a x, new x. And E1 and E1 dash is a different. This is a, we can think this is a case we have a rotation of coordinate system, right? So we can think coordinate system is changed. But very interesting, important thing is that the current position can be expressed by x1, E1 plus x2, E2 plus x3, E3. Is that you understand? Base vector is changed, but the component is still same. Right? So the distance between x and y axis is same here and here. Even because just the coordinate system is rotated. And then here we know the relation between base vector E1 equal cosine zeta E1 minus sine zeta E2. E2 equal sine zeta E1 plus cosine zeta E2. E3. You know this, why we have this relation? Okay, so for example, E1, E2, and this is a E1 and zeta. So all the base vector have a unit magnitude 1, right? So it has a ranks 1, okay, and zeta. What's this amount of distance? Okay, cosine zeta. And this is sine zeta. So E1 equal cosine zeta E1 minus sine zeta E2. Similarly, we can calculate second equation. And let's put this relation here, here, and here. Then x become x1 cosine zeta plus x2 sine zeta E1 plus minus x1 sine zeta plus x2 cosine zeta E2 plus x3 E3. And here the first term become current position x1. Second term x2, third term x3. So that we found out the relation between small x and big X. So x1 equal x1 cosine zeta plus x2 sine zeta. x2 equal minus x1 sine zeta plus x2 cosine zeta. x3 equal x3. What's the deformation tensor? 정호. Now you can find out deformation tensor, right? Can you write down the deformation tensor here? Based on this equation. Yeah. Yeah, is that correct? Is that right? Yeah, I think this is right. Very easy, right? But how about in the last class? This is too simple, right? This is a very, very well-known rotation matrix, R. So, when a body is under the rigid body rotation, okay, this is a deformation matrix, become a rotation matrix R. So, R it has a name, rotation matrix. Okay, so let's calculate J. J is a determinant of F, determinant of R. What's this? Cosine square plus sine square equal 1. So J equal 1 during the rigid body rotation. It means there is no volume change. Okay, volume is the same. No volume change. Change. So other way. And rotation matrix have a very interesting characteristic. Its transpose is same to its inverse. Inverse and transpose is same. So it means if you multiply transpose of rotation matrix, and this rotation matrix give us identity matrix. So you can prove very easily. Inverse of the rotation matrix mean the rotation in the other direction. So body rotate and go back to the original position. So when there is no displacement, so let's say, for example, this is a initial body, omega, and same, no displacement. Current body and initial body is same. Then what's the deformation tensor? It means x1 equal x1, x2 equal x2, x3 equal x3. Deformation tensor become identity. Right? So let's say we have initially body here, omega. And after some time, this body changed, omega t. So, for example, let's consider this simple deformation. This is just one step deformation. Then we can decompose this deformation in two parts. So this body first stretched. Okay? And then this stretched one. So for example, something like that. Stretched one, rotate. Zeta. Then we can have a same result. Let's say this is a deformation tensor F. Okay? And stretch first, stretch tensor D, and rotation tensor from here to here, R. So, in general, when we have a deformation tensor F, this deformation tensor can be decomposed by two parts, R and D. And R is the rotation tensor or metric. D is a stretch tensor. This is a polar decomposition. We can decompose the deformation gradient into rotation and stretch. This is polar decomposition. Okay, this is very, very important concept. Also, we can think F equal, here the stretch first, but rotation first, and stretch second. Same thing. Okay? Here, deformation first, stretch first, and then body is rotated. Body is stretched and then rotated. Here, body is rotated and stretched. Same result. But this D and this D are different. This R and this R is different. Okay? In general. Okay, so let's finish the lecture today. So, any question?